No, I'm still not gonna have an intro. Fight me about it. Yes, I'm back. I'm here for the part 2. Don't worry. I wouldn't leave you hanging. So, I will give you a little bit of a warning. Last video took way too long. So, I'm going to try and make this video as concise as possible. Basically, I'm going to be giving even shorter summaries and recaps of every single chapter because I don't want this video to be 20 minutes long. Although it probably will. On that note, let's just get straight into it. Also, if the lighting changes while the video is going, don't question it. I'm currently filming this while it's like afternoon, evening, and so the sun might set in the middle of filming. And if it just gets dark and the quality of the video suddenly goes down, just know it's not my fault, it's the sun's. Anyways, into the video. So we start with Newton, who basically invented what is now differential calculus. He also was the father of physics, but we don't really care about physics because this is math. So, my notes almost fell. Lovely. What happens is he uses what are called fluxions to help him basically not invent, but kind of create the way to do differential calculus. He doesn't necessarily publish a bunch of his work, though, and this gets complicated as we move into chapter 21. But we'll get there. He doesn't publish a lot of his work because at first he tries to publish it, but then a bunch of people are like, ew, what is this? So he doesn't publish a lot of it. On to the messy stuff in chapter 21. So basically, in chapter 21, there's this one guy, Leibniz, I think is how you pronounce it, I'm not sure. So Newton didn't publish a bunch of his work, Leibniz did. And he also stole some of Newton's work and put it in his own writing. You know, yay, plagiarism. And teachers say it's a bad thing. Look at him go, he got famous off it. But there's a bunch of controversy over like, ooh, who did what and who deserves credit. It doesn't really matter. It's just mathematicians arguing, which as we know is just pointless to the rest of us normal people. But this does bring up there are two different approaches to mathematics. So Newton used fluxions, Leibniz used infinitesimals, which is different. They have different ways of writing it. So it has some interesting things when you actually get down to the math of it, but we don't really care. So it also causes a schism between mathematicians in Great Britain and mainland Europe. Yay! More pointless arguing over numbers. I'm tired. Let's just move on to chapter 22. So chapter 22 is about like calculus catching on and like spreading a bit. Basically what happens is people start writing textbooks about calculus, you know, to torture the rest of humanity. People like Agnesi and like the Marquis and Euler, they start writing textbooks and they, you know, start spreading like the ideas of calculus. But, you know, there's a bit of an issue and it's brought up by this man called Bishop Berkeley. Basically, he's like, okay, so infinitesimals and fluxions are stupid because they break our understanding of reality. The idea that like something can be so small that it doesn't amount to anything despite adding infinitely many of them is stupid. And fluxions being unseeable is stupid. So calculus is dumb, and to be honest, I kind of agree with him. But don't let my math teacher hear this or I might go missing. So yeah, that's chapter 22. So chapter 23 is all about Pascal, and basically this man works in probability theory. So, you know, gambling, woohoo, let's go. So Pascal really works a lot in probability theory. He also uses it to prove that God exists, ... no comment. And that's fun. But also Pascal's triangle, super cool. If you want, Google that. It's a really cool thing and it's so much fun. And then finally, Pascal, he not necessarily invents, but like he brings to light the cycloid. If you take a point on the circumference of any wheel and then roll that wheel along the ground, the shape that is traced out by that point is called a cycloid, and they get important later. So yeah, that's chapter 23, all about Pascal. He's a cool guy. I like him purely based off of intuition. Judge me for it. But we gotta move on to chapter 24. So chapter 24 is all about the Bernoulli family. Yeah, it's a family of mathematicians. I think at this point I'd be okay with murder of the entire family. But I can't do that, because time travel, duh. So basically, the Bernoullis, bunch of smart people. They dominate math, super smart family. They do a bunch of stuff. Basically, the biggest thing that we care about, though, is the other half of the page of the chapter, where it talks all about the brachistochrone problem and the tautochrone problem. Basically, the brachistochrone problem is if you have 2 points in a plane, what is the path of quickest descent based on gravity alone? So, like, if I drop a ball at point A, what is the fastest way to get it to point B? And basically, the solution to the brachistochrone problem is actually a cycloid, which was discovered earlier, as we just talked about. So yeah, that's pretty cool. And then the tautochrone problem, which has the same solution. It's a cycloid. Basically, if you put 2 marbles on any point on the brachistochrone, they will get to point B at the same time. So yeah, cycloids are the solution to everything. Don't quote me on that, please. And on that, we're moving on to chapter 25. Okay, chapter 25 is also blank. I don't know what they were doing, but it's blank. Basically, though, just from, like, the printed out notes, I can tell you it includes things like Snell's law, which, you know, I guess that exists. And it's just them proving that the cycloid is the answer to the brachistochrone problem. So, yeah, not much else to say besides, yeah, the Bernoullis got the answer correct. Woohoo! And that's chapter 25. So chapter 26 is back to number theory. Yay! Nobody's happy. But basically, this time it's number theory concerning 2 special people. So the first one is Mersenne, and then the second one is Fermat. So starting with Mersenne, basically this guy just does more number theory stuff. He studies relationships between all the numbers. He's like studying primes and like how to find them. All that fun stuff. And that's Mersenne. He does make a couple mistakes in his work, and then, you know, they're, of course, referenced in this. But we still stan him. And then moving on to Fermat, who was like an amateur mathematician because he had a life outside of math, which is also just known as having a life. But also, in one of his writings, he leaves like a cryptic note that like, I have a solution to this one problem. The problem is, if you take the Pythagorean theorem, you know, a squared plus b squared is equal to c squared, can you change the exponents to be any integer greater than 2? And can you find a solution for that? We don't know. He said he had a super simple solution to it, but we have proved it now, and it's not simple, so we don't know what he was doing. But yeah, that's this chapter. Moving on. So chapter 27 is all about Euler. Yeah, it's Euler, not Euler. I learned that. I didn't even know who he was before this, so yeah, that was fun. But he does a lot in math. Not enough to cover, as it says in the notes, so just the basics are covered. So there's like Euler's constant, and there's also like a bunch of stuff that he did to help develop calculus. You know, like I said, he wrote a textbook on it. So I think he knows just a little bit. But one thing that he also does is he also solves the Königsberg bridges problem by thinking of it as points or vertices and edges in a shape instead of like islands and bridges. And he proves that they cannot, in fact, cross every bridge once to reach each island. So, suffer is what he said, basically. We stand, though. And then also, it moves on, and he studied, like, the relationships between prime numbers and how it pertains to, like, the Riemann zeta function, and I have no clue what they're talking about. Like, I would genuinely try to explain it, but I genuinely don't understand any of this math, and half of it is not filled out, so yeah, I have no clue what's happening. Just like for most of this book. But we gotta move on. So, that was chapter 27. So chapter 28 is all about Gauss, and basically it's everything that he did, because he did a lot. He was a really amazing mathematician, according to the notes. I don't know. Like I said, I barely know what's going on. But basically, he does a lot of work in every field of math, which is crazy because every single field of math is completely separate from all the other fields. So things like geometry, algebra, statistics, analysis, all of it. He does work everywhere, and he's a genius about it. You know, I will say, he does a lot more than I am listing here, and like, there is so much in the notes. I genuinely can't fit it all, but there's just a lot. Like, a lot. And I can't list it all. So just know he was super smart. He did a lot for math. We gotta move on. have fun with that. So chapter 30 is about complex analysis, and there's this guy, his name is Kachi. I think that's how you pronounce it. I'm probably wrong. But first thing that he does is he standardizes what is stuff. So like he sets down the definition of like a limit or like continuity or derivatives and integrals and stuff like that, which is super important for the development of calculus. Moving on with more complex analysis, it's honestly, like I said, about the stuff that he set definitions about. So continuity, limits, getting closer but like never truly touching, like my siblings playing that one game. Fun. Also, it introduces the Cauchy-Riemann equations, which I can't explain. I don't even understand what half of these symbols mean, but just know that they exist and they're important. And that's chapter 30. So chapter 31 is all about an intro to modern algebra. And part of that includes the introduction of rings, groups, and fields. And it talks a lot about them and their properties and the things that define them and all of that. And I really wish I could understand it because it sounds very interesting. But they lose me so fast anytime I try to read it. But it's an intro to modern algebra, so yeah. Rings, groups, fields, and then also things like subgroups or like different types of rings or like fields and field extensions and all that complicated stuff that defines modern algebra that I can't explain because I am, once again, stupid and illiterate. But yeah, that's chapter 31. So chapter 32 gets complicated. Basically, chapter 32 is an intro to algebraic number theory. Yeah, as if math wasn't bad enough, we're just gonna start combining these literal demons. So, basically, what this one is it's complicated, because whether it's more algebra or whether it's more number theory is disputed. But basically, if I understand it correctly, which I probably don't, and this is gonna be a gross oversimplification, but it's all to do with the relationships of numbers and how they relate in between like their sets, their groups, their fields, and all of that. So like how integers relate with other integers and like real numbers and stuff like that. It's weird. And that's all I can say about it. So chapter 33 is modern set theory part 1. This is 1 out of 3. Once again, most of these are going to be gross oversimplifications because I don't know what I'm talking about. So just keep that in mind and take everything I say with a grain of salt. And if someone tells you otherwise, I would trust them. Basically, this one is where we attempt to describe real numbers. Fun! Also how numbers interact within like sets and groups and fields. Kind of like the last one, but not really. It's set theory. So sets. We're taking sets and we're analyzing them and we're studying them. How they work, what are the relationships between them, and basically it sets out the basis for what set theory is what this chapter is. So there's stuff like what are real numbers and Cantor sets made by this guy. They're sets made by Cantor. And that's modern set theory, part 1. Part 2 of modern set theory is chapter 34. And this chapter covers more about Cantor and also another guy, Russell. Basically, they continue to work in this field of mathematics, but they also cause a bunch of other issues. So one example of this being cardinal and ordinal numbers, which have some contradictions and they're kind of confusing. I'd love to explain it, but I really sound like a broken record. I don't know what's happening here. But cardinal and ordinal numbers have some issues, so that doesn't really work. And also, Russell proposes a paradox, that's the Barber of Seville, which, reflects some of the issues that were within set theory at the time. Basically, gross oversimplification, the Barber of Seville shaves everyone who doesn't shave themselves, who shaves the Barber of Seville. It's complicated. And that's modern set theory part 2, except at the end we get introduced to this one guy, Hilbert. And he, at the 1900s Congress of Mathematics, proposes 23 problems that mathematics needs to solve to advance. And they're horrific, disgusting, but basically they lay the groundwork for, okay, what do we need to work on for math to grow and become better? That's modern set theory part 2. So we've been having some issues in math, there's some, like, issues and, like, Hilbert and his 23 problems that are showing all the flaws within mathematics. So basically, everyone's struggling trying to find axioms that are gonna make math work again. And that's basically the beginning of the 35th chapter, Modern Set Theory, Part 3, which is the final part, thankfully. Once again, that's kind of the beginning, not really, but it's very oversimplified. However, it also introduces the axiom of choice. Basically, if you have infinitely many mathematical drawers, can you open every single drawer and take out a singular item? Sounds simple, there's some issues. So one issue with this is the Banach-Tarski theorem, where if you take a sphere, cut it finitely many times, and then just translate and rotate the pieces, you can get two identical, fully complete spheres. Yeah, so bit of an issue if that's true. And so everyone's like freaking out, and then there's this guy, Gödel. As if math didn't have enough problems, he shows up, and he basically proves we don't know what the limits of our knowledge are, and there is no way to figure it out. And it basically blows everyone's mind, and yeah, it kind of just completely messes with our perception of math. So everyone's suffering, which honestly, mathematicians deserve it. Like I said in the beginning, I apologize for the lighting. The sun has set. It is not my choice. If I could, I would have prolonged it. But we're just going to power on to the end of this. So chapter 36 is all about topology. So yay! Math and maps and how that works. The graphing of places. So geometry and graphing and like, that's math. But like, maps. Topology. That's basically chapter 36 in a nutshell. Oh, and also, my favorite thing in the entire world, the ham sandwich theorem, okay? If you don't know the ham sandwich theorem, you're about to learn. Basically, if you take the ingredients within a ham sandwich and position them anywhere in a 3D space, there is a plane, there will always be a plane that exists where you can cut all of the pieces in half perfectly. Let's go. Math for the win with my sandwiches. Chapter 37 reverts back to the first chapter, the philosophy of mathematics. It reverts back to it in the sense that after everything that you've learned, after you've seen how math has grown and how these beliefs and like these arguments have shaped and developed math, how they have impacted math and how math has impacted these beliefs. And I think that's actually a really cool thing. Ooh, all philosophical. I really don't care. But I think it was an interesting tie back and a nice way to almost end the class. Chapter 38, though, basically, it's literally called, like, mathematical curiosities. It just kind of opens the door to, like, well, have fun now. Like, it presents some of the, ooh, there's more stuff to math. Here are some amazing modern mathematicians that existed very recently and have come up with crazy things. And here are some interesting things about math. And here are, like, some unsolved problems. And I think that's a great way to end this. Kind of, not inspirational, but almost urging them to go on, to go out, and be a part of modern mathematics. So, yeah, this ended on a much more wholesome note than I meant to. Let's revert back to the last video. Math cult, math cult. Just kidding. I won't be starting a math cult until school starts. Then I can get more members. Well, I think that's everything. The sun has set, my day has ended, the notes are finally finished. So yeah, that was an unhinged recap of my math teacher's college-level math notes. Maybe subscribe, maybe like. This took me work and effort, and I think it might be, probably isn't. No, it really isn't funny. But you could send help. Please send help. Anyways, enjoy your life.